The topic we're going to talk about today is nuclear reactions. Now, all the reactions we looked at in this course thus far have been chemical reactions. Now, the chemical reactions involve the rearrangements of electrons. It's that movement of electrons that creates the new compounds or breaks the compounds apart. What makes nuclear reactions different is we're not looking at the electron rearrangement, but we're looking at the rearrangement of protons and neutrons. And it's that rearrangement that causes new products to be formed. Now, nuclear reactions, when they occur, they release a massive amount of energy. We know this energy to be known as radiation. Now, when we're writing the equations out, we need to remember that we have a reactant side and a product side, just like a normal chemical reaction. And the reactant side, in terms of mass, must equal the product side. And the sum of the atomic numbers must balance. So the atomic number on the left side must be equal to the atomic number on the right side. This is the law of conservation of mass. Let's take a look at an example here. And the first example we're going to take a look is an alpha decay. An alpha particle is simply a helium particle with no electrons. So let's take a look at a few examples here. Our first example here is 22688 radium. Now, when that breaks down, it shoots off an alpha particle. So 42He. From there, we've got a new product. Now, this product, remember, the masses have to stay the same. So we know on the left-hand side, the mass of this equation is 226. We know the mass on the right-hand side is 4. Therefore, the new mass of our particle has to be 222. Let's say we're talking about the atomic number. We know the atomic number on the left-hand side is 88. And on the left-hand side, we know the alpha particle has 2 protons associated with it. Therefore, our new product is going to have 86 protons. And if we take a look on our periodic table, we'll see that corresponds to radon. Take a moment and try the next example on your own before you continue. For our next example here, we have 25299 Einsteinium. Now what happens is that's going to undergo alpha decay. So 42He. It's going to have a new product. Now the masses on the reactant side have to equal the masses on the product side. So the reactant side, it's equal to 252. On the product side, the mass right now is equal to 4. So therefore we know the answer has to be 248. It has to have a mass of 248. If we're looking at the number of protons, we know on the left-hand side we've got 99 protons. On the right side, we've got 2 protons. Therefore, our new product is going to have 97 protons. Now, if we take a look at our periodic table, we will see that as berkelium. Now, if we take a look at the third reaction we have right here, we have nothing on the reactant side. We simply have the product side. Now, the product side we know is equal to 248 plus 4. This means that our reactant side has to be equal to 252. We know berkelium has 97 protons and helium has 2 protons. So 97 and 2 makes that equal to 99. 99 is Einsteinium. We can see this third example here is simply reverse of the example above. The next example we're going to talk about here is beta decay. Beta decay works in a similar fashion. An atom loses a beta particle. A beta particle is known as simply an electron. So let's take a look at some examples here. We've got radium right here is our first example. And we're going to follow the same logic as before. It's going to undergo a beta particle. Plus it has to undergo something new. So the mass side is easy. The mass on the left-hand side is 226. The mass on the right-hand side for the electron is 0. Therefore, our total is 226. Now, if we're talking number of protons, we've got 88 protons on the left side. The right side, we've got -1. When you subtract a negative, it becomes positive. Therefore, our new element right here is going to have 89 protons. And according to our periodic table, that's actinium. And if you want to check the math, 89 plus -1 is 88. Try the next example on your own. For our second example right here, we've got 25299 Einsteinium. It is going to eject a beta particle. We're going to have a new item here. The math is easy enough. It's 252 as its mass. 99 plus -1, or sorry, subtract -1, that becomes 100. And if we take a look on our periodic table, the 100th element is fermium. For our third example here, we've got 248 and 0. Therefore, we know the reactant side, the mass is going to be 248. For our third one, we've got 97 and -1. That is equal to 96. If we take a look on our periodic table, 96 is curium, so Cm. Gamma radiation accompanies most nuclear reactions. We don't always necessarily write it because it has a mass of 0 and 0 protons, so it doesn't affect the molecular shape. But it usually does occur, it's just an energy release. So I'll do the first example right here. Cesium-137 undergoes beta decay and releases gamma radiation. So cesium-137, if we take a look on our periodic table, cesium has 55 protons. It's undergoing beta decay. A beta particle is 0, -1 electron. Plus, it releases gamma radiation. There also now has to be a third particle. We know from the fact that there's 0 mass to the electron and 0 mass to the gamma radiation that the mass is still going to be 137. Because of this electron right here, we know this is going to become 56. And if we take a look in our periodic table, 56 is barium. Try the next example. Take a moment and try the next example on your own. Okay, our next example here is 24195 americanium. Now it says it undergoes alpha decay, and an alpha particle is 42 helium, and it releases gamma radiation. Now we have to figure out what the third particle is going to look like. We can see that we have 241 here, we've got 4 here. This is going to become 237. We know we're starting with 95. We subtract 2. That becomes 93. And if we take a look on our periodic table, 93 is neptunium.